Good afternoon, everyone. We'll start in a few minutes. We'll wait for a few people to join, and then we'll begin. Okay, we'll begin now. Thank you, all of you, to come and join for today's discussion. Someone please confirm if my screen is visible and I am audible.
Yes, Silas.
Okay, thank you, sir. So today we are discussing about geosynthetic solutions for river and coastal protection works. We'll try to cover all the discussion within 1 hour, and we'll take all your questions after the presentation. So please put your questions in the chat box. We'll answer them after the presentation. I'll begin with the overview of TechFab India. So we at TechFab India, we started in year 2003. We started with a dream to give India world-class geosynthetic products. We started with a modest beginning while setting up a Bhuvan geotextile manufacturing plant at Silvassa. And today we are very proud that we have rapidly grown to become the largest manufacturer of geosynthetic products in India. Today we are having 6 factories located all across India. Our factories are located at Daman, Rakholi, Athal, Kharoli, Karajgaon, and Haridwar. We have 2 units at Daman, and we have a very soon we have upcoming unit at Bhopal. So total we have 8 manufacturing facilities in India. Our manufacturing facilities, products, and our laboratories are certified with various testing facilities, various accreditation certifications such as BIS certification for various products, and then NABL certification for laboratory, ISO certification for manufacturing facilities, and various other international certifications like SKJ and BTTG certification as well, which are applicable in European countries. So the design and safety of waterfront systems, it poses very unique challenge before all of us, like engineers, contractors, and manufacturers. Why? Because waterfront systems are mostly applicable to high flow rate, wave impact, sudden drawdown, surface erosion, and various other site-specific issues. And many of these issues come together at many places. That makes the problem very unique and complex as well. So these unique problems require unique solutions which should be sustainable and economical as well. So these geosynthetic products help us to provide effective design solutions for most of the structures, waterfront structures, which are coastal river protection works, canal lining, CD works, and several other irrigation and hydraulic structures and other water infrastructure. We'll discuss one by one the design procedure and the product wise. So the geotextile materials of the products mainly are 2 types. One is woven geotextile and non-woven geotextile. These woven and non-woven geotextile are either manufactured by either polyester or polypropylene. These polyester and polypropylene are the mostly followed or the mostly used geotextile material for the manufacturing of woven and geotextile, but these are not limited to these only. Some other polymers like polyamide are also used, but PET and PP are mostly used for manufacturing of woven and non-woven. Like polypropylene fibers, they are lighter than water, having specific gravity of 0.9. They are strong and durable. And the PET or the polyester fibers, they are heavier than water, having a specific gravity 1.297. So they are the inherent properties of the polyester fibers are to provide us better strength as compared to the polypropylene fiber. So whenever there is a strength requirement, polyester fibers or the polyester made geosynthetic products are mostly used. Whenever polypropylene fibers are used, they will give us better durability. But again, they both are good, durable, and strong as well. But when it comes to the extreme end of strength requirement and durability requirement, PP should be given preference for durability and PET should be given preference for strength. We'll discuss these 5 products in our presentation today, which are metal gabions, can be in the form of box, mattress, or sack gabion. Then sand-filled geotextile mattress. Then concrete canvas, which is a new product. We will discuss about it. Then sand-filled geotextile bags and geotextile tubes. Now, what kind of solution is to be proposed for a particular site? It depends on various factors such as topography, soil parameters, hydraulic parameter of the location, site-specific requirement, and material availability. Like topography, if my river water channel is located on the headwaters or the upper regions or the upper terrains, these water channels will be susceptible to high velocity and lower in the lower reaches, the velocity may be higher or lower, but the discharge value will be higher as compared to the headwater or the upper reaches. So this plays a very big role in deciding the solutions. Then soil parameters, hydraulic parameters, we all know play a very big role. Site specific requirement and material ability. For example, if a location, for example, Sikkim, which is having abundant rock available in the vicinity, then we can also propose the Gabion or the rockfill solutions. But some locations, like some locations in the Brahmaputra River basin, okay, these locations are not available with, not equipped with the rockfill, but they have abundant sand available. So now we can propose the sand fill solutions. Therefore, this material ability plays a very big role. So now we'll again come back to basics and then we'll proceed with understanding the designing procedure. So we'll understand the brief of floods, which occurs when the river water spills out of the banks and it gets submerged in the nearby areas that damages the infrastructure, human lives, agriculture, and various other factors also it causes to our lives. And these days, the very severe concern for all of us, the engineers involved in the water resources industry, are the flash floods that we are frequently seeing in the upper regions of India or the north regions or the northeastern regions like Uttarakhand and Himachal Pradesh. Flash floods are occurring very frequently. Even this year also it is occurring, like minor flash flood has also occurred in Kedarnath a few days back. So it can occur when a excessively heavy rainfall occurs in a very short period of time, which can be less than 6 hours. It can also occur within a minutes or within few hours, like for example, cloudburst. And they can also occur when there is a sudden release of dam water or breach of dam. So all these heavy flood situations, they causes the riverbank erosion to us. So high flood discharge leads to high flow velocity, and this high flow velocity gives us the tractive shear force in the direction of the flow. That tractive shear force occurs on the river bed and side slopes both. Now, when the induced shear stress is more than the permissible shear stress, That means it is more than that means it will cause you the erosion, because whenever there is an induced shear stress more than permissible shear stress, then the soil particle on the river channel will start migration from its position. And this migration procedure is in most of the condition is a progressive procedure. So this migration of the particles of the soil particles from the bed or slopes will cause progressive soil erosion. So other than the tractive shear stress or the heavy flood, other causes are also there for the riverbank failure. For example, global wedge failure, then sudden drawdown, toe failure due to scoring, and then piping in the sublayers. The picture you are seeing here is a is a example of global wedge failure you can see here. So now we have understood the brief of the problem. So now what are the possible solutions for riverbank failure? The solutions can be direct protection work or indirect protection work. Direct protection work are also known as surface measures. They are applicable only on the stable, geotechnically stable slopes. The surface protection work does not impart any structural stability to the system. They are applicable on the geotechnically stable slopes. If if the if the surface or the slope is not geotechnically stable, then we have to make some measures to make the slope stable. So now the surface measures are can be concrete lining, Gabion mattress placement on the slope, then geotextile sand mattress, geotextile sand bags, geocell, then vegetative cover, etc. Indirect protection work are called the protection work that are not directly provided on the banks, but they are provided in front of them. For example, launching aprons, spurs, gryons. They are provided on the ahead of the structure, ahead of the main slopes. For example, indirect protection work, for example, are the launching apron, spurs, and gryons. The gryons, as we all know, can be deflecting gryons, attracting gryons, sedimentation gryons as well. As the picture in the picture you see, they are the they are the straight gryons which are also used for sedimentation. So these the purpose of the indirect protection work are to provide to keep the flow away from the banks and prevent the development of score holes. So now we'll understand the design procedure of the Gabion mattress riverbank protection system. As we said that it is applicable on the geotechnically stable slopes. So the guidelines for the Gabion mattress riverbank protection are mentioned in IRCSP 116. The critical inputs required to proceed with the design are the design discharge, cubic meter per second, then river geometry, which includes cross section, river bed gradient, then geotechnical survey report, which includes the grain size analysis, silt factor, and shear parameters, and some other properties of the soil. And also, we should keep in mind that whenever we have a geotechnical survey report for the riverbank protection work, at least one borehole should be provided, which should be inside the water periphery or the water surface area or the inside the river boundaries, not only on the banks, because it has been observed at many places that there is a huge variation in the bank soil or the river bed soil, because in most of the cases river bed soil is the alluvial or the migrable soil. That's why. So, but again, the borehole will give you the subsurface properties. Uh, so also then, other than the soil report, we need hydraulic parameters such as HFL and low water level, and then again the material availability. Other than this, we also need to know if there is any additional surcharge or the loading on the bund level or the top of the bund level. For example, here we need to know if there is any inspection path or non-inspection path is available, then we need to take care of the loadings. Now, the design is based on the tractive shear force theory. So the tractive force theory assumes that there is an actual shear stress which has been already exceeded the permissible shear stress, and a dynamic transport of the colloidal aggregates occurred. So that is the reason why we are looking for a solution for the riverbank protection, because the actual shear stress has already exceeded the permissible shear stress, and the migration of the particles are already started. So first we need to calculate. So once it is done, then we need to calculate the induced shear stress. Now induced shear stress is calculated using this formula, which is tau b is equal to K1 Kb gamma y into SF. SF is the river bed gradient. Y is the depth of the flow. Gamma is the unit weight of the water. K1 Kb are the coefficient, slow factor and band coefficient. These details are also available in IRCSP 116. Then first, now we have calculated the induced shear stress, which is the actual shear stress. Now we need to calculate the permissible shear stress. Now permissible shear stress we need after placement of the Gabian matrix. We have assumed that we are providing a Gabian matrix. Now we need to know what kind of median diameter we need to know. So now tau c is the KSCS gamma S minus gamma W, which is submerged unit weight of the soil. Then D50 is the median diameter of the rockfill in the matrix. How to calculate the median diameter we will discuss in the upcoming slides. Then gamma S minus gamma W is the submerged weight of the rockfill boulders. Then Ks is the reduction factor, Cs is the shield, which is equal to 0.1. So now we have calculated the tau b and we have calculated the tau c. So now for a safe section against the attractive shear stress, induced shear should always be lesser than the permissible shear stress. Then our solution of the Gabian matrix protection system will be stable. You can see in the picture the maximum induced shear stress is always there on the river bed, because maximum height of the water is always calculated from the river bed. Whenever we go near the HFL or the water level, the induced shear stress is as low as 0. And the maximum shear stress is always on the bed. So the susceptibility of the erosion starts from the river bed. So now we have decided that we need to provide a Gabian mattress on the slope. First, we check whether there is a problem that needs to be taken care of. Then we have decided that we are providing a Gabian mattress protection system. Now the thickness of the Gabian will be decided based on the following factors, such as erodibility of the bank soil, means soil type, then velocity of the water flow, and then bank slope. Non-one geotextile will always be provided on the interface of the soil and Gabian matrix system. So in this, this table is also available in the IRC 116. You can see that the critical thing to look into this table is whenever there is a bank slope steeper than 1:2, which is 2H to 1B. Whenever there is a steeper slope of whenever there is a slope steeper than 1:2, be it any type of bank soil, then the minimum thickness required will be more than 450 mm. So in this case, the requirement of the requirement of the Gabian matrix thickness will be 450 mm. And if the bank slope is milder than 1:2, then we need to check the maximum velocity criteria and the bank soil criteria and check the requirement of the thickness for the mattress. So this is how we decide the thickness of the mattress. Now we have decided the solution on the slope. Now upcoming task is to design the launching apron. Launching apron, as we discussed in the previous slide, will be provided in the direction perpendicular to the flow, which will be in the direction of the slope. The launching apron is provided on the LWL or the low water level or river water level in most of the conditions. Non-one geotextile will be provided on the interface of the river bed, and we need to understand that non-one geotextile will always be provided as a separator or filter on the interface of soil and any kind of protection system, which is permeable protection system. So this is why non-one geotextile will be provided on the river bed and launching apron, which act as a filter and separator. And it prevents the migration of soil particles from soil surface or the soil embankment to the protection system, which is the Gabian mattress. Thickness of the launching apron will be decided or considered 20 to 50% more than the bank protection thickness. If we have provided 450 mm mattress on the bank, it will be provided around 600 mm or more than that launching apron thickness. Score depth, but again, if we are providing toe trench or toe key, it can be compromised. The thickness of the mattress can be compromised as well. So there are various other factors we'll see in the cross sections, and the other detailing. Now, score depth, for designing of the launching apron, the first step is to check the score depth. Score depth is governed by various factors such as maximum flood discharge, HFL, and channel geometry and subsoil characteristics. Subsoil characteristics means gradation or the silt factor. Normal score depth calculation, there are, for the calculation of normal score depth, there are two formulas available. In IRC 116, only equation 1, you can see there are two equations I have mentioned here, but IRC 116 only gives you one equation number 1 only. But if you see in SP 13 or SP 89, IRC 89, then it will give you two formulas to calculate the launching apron. We'll understand both the formulas here, and we'll know in what conditions which formula should be used. So the normal score depth calculation is decided based on the looseness factor. Now, calculation of looseness factor is the calculated using this formula, which is overall width of the river divided by Lacey's waterway theory. Lacey's waterway. So Lacey's waterway theory says that the waterway is calculated using this formula, which is P is equal to 484.83 under root Q. I'm just giving one example. For example, if the discharge of any river water channel, which is Q, equal to 10,000, just giving a random value, which should be easy to calculate. If the Q value is 10,000, under root Q is 100, then the Lacey's waterway P is 483 meter. Now, if my actual overall width of the river is more than 483, then looseness factor will be more than 1. If my actual width of the river is less than 483, then looseness factor will be less than 1. So if the looseness factor is more than 1, means the width of the river is more than the Lacey's waterway width, then the river will be called a wider river. If the width of the river is less than 483, 483 is only when Q is 10,000. So if the looseness factor is less than 1 or the width of the river is less than 483, then the river will be called as narrow river. For example, if you see the Brahmaputra river, the width of the river is very huge as compared to the Lacey's waterway. So in the Brahmaputra river basin, in most of the cases, this formula will be applicable. But if you see in the upper reaches like Himalaya or the Tista river or in Sikkim area, then the overall width of the river is lesser than the Lacey's waterway. In those conditions, in most of the cases, this formula is used. So why this formula is used when there is a width of the river lesser than the waterway, means there is a narrow river. Because whenever there is a narrow river, then the critical parameter is the unit discharge becomes the critical parameter, and whenever there is a wider river, then actual discharge becomes the unit parameter, the critical parameter. That is why in the wider rivers, the formula is 0.473 capital Q by F power 1 by 3. F is the silt factor. And in the second formula, it is small q square by F power 1 by 3, which is small q means capital Q divided by B. So it is mentioned here, intensity of the flood discharge per meter width of the river. So this is how we calculate the formula. We calculate the normal score depth. So we have understood the way of calculation of normal score depth, but there is a catch that normal score depth is having no significance in the direct calculation of launching apron, because we always need to calculate the maximum score depth, and maximum score depth is always a factor multiplication by normal score depth. We never use the normal score depth for the calculation of any protection system. So now, as per IRC 116, the factor is 1.5 times, the factor is 1.5. So maximum score depth is calculated as 1.5 times of normal score depth. Now maximum score depth is calculated below. So this formula will give you the score depth below HFL. Now we need to calculate this delta Z value, which is calculated from this from the page from the riverbed level to the maximum scoreable portion. For example, just again I'm giving one example for understanding purpose only. If the normal score depth, for example, if it is a 6 meter, this let's say normal escort depth D is 6 meter. If it is 6 meter, then it will become 9 meter. Let's say if this is the river bed level here, if it is 100, and my maximum water level or HFL, let's say if it is 105, if it is 105 meter, okay, if it is the case, then 9 meter is the maximum score depth. So now I need to calculate the maximum anticipated depth of the score, which is 9 meter from HFL. So 105 minus 9 will become 96 meter. So 96 meter is will come here, which is 96. Okay. So now delta Z is the delta Z will be only 4 meter. So which is 100 minus 96. So now delta Z is 4 meter. I need to calculate the width of the launching apron, which is 1.5 times to 2 times of delta Z. So in this case, if it is 4 meter, then width of the launching apron will be 6 meter to 8 meter. So in most of the cases, we consider it 2 times of the maximum anticipated depth of the score. So in this condition or with these parameters, the width of the launching apron will be 8 meter. I hope you all understood the design of launching apron. This is one typical cross section of design of launching apron. So now we have, since we this is a little bit out of the scope, but since we are discussing the score depth conditions, we also need to know about the bridge pier and abutment scoring. So this is also part of the water infrastructure. Whenever there is a need for bridge and abutment protection, bridge pier and abutment protection, because they are heavily susceptible to scoring, as we have recently seen in the Bihar. At the time of onset of monsoon, there are several bridges they have shuttered down. If you look closely, the reason will be because the foundation of the most of the piers was getting exposed, and the maximum anticipated score depth was below the peer foundation. That is the reason. That is one of the many other reasons for the failure of the river bridges. So in this condition, the maximum score depth is calculated while should be calculated while designing the pier and abutment foundation. As per SP13, maximum score depth is calculated for pier and abutment. So the way of calculation of the normal score depth remains same, but the factor of multiplication or the maximum score depth is calculated with using these factors. So maximum score depth for piers will be 2 times of normal score depth, and for abutment it will be 1.27 times of score depth. So this is how the score hole gets developed, and we need to protect the river foundation. The first way of designing, first way at the time of designing of the river, at the time of designing of the pier and abutment, we need to check the river maximum anticipated depth of the score, and then the foundation should be placed well below that. If it is not the case, then we need to have a protection system all around the pier foundation. So in those conditions, sand-filled geotextile bags, geotextile mattress, gabion mattress can be placed all around the pier foundation or the abutment foundation, so that we can prevent the development of spores. You can see one protection system is being is encapsulating the abutment. This is one case study of where we at TechFab India provided Gabion mattress for the Sardar Sarovar Dam, Statue of Unity, on the downstream of Sardar Sarovar Dam at the Statue of Unity. You can see the pictures at the time of construction, and you can see the right hand side pictures at the time of execution, or at the time of severe monsoon or the dam when the dam gates were opened. It is working very fine. I urge all of you, whenever you go to Statue of Unity, you visit the site and see how it is being installed at the site. So now we have understood the riverbank erosion, then launching apron design, then need of protection work on the launching apron. Now, and Gabion mattress low protection. Now we are understanding a brief of design principles. Since we have limitations of the time, we need to I'll give you the brief of design principles of the Gabion gravity wall. So again, the procedures of the design, the detailed procedure of the design is mentioned in IRC 116, and it is designed on the same principle as Gabian of the gravity mass wall. That is based on the limit state principle, and the objective is the Gabian mesh should hold the rock mass within the limited deformation, which should not affect the aesthetics and internal stability. So now, based on the site requirements, Gabion walls can be designed with several configurations, such as stepped outside. You can see this is the stepping outside, then stepped inside. You can see here in the stepping inside, and then offside on the and then offset on the both side. Okay. Then also with and without better angle, you can see the first picture. There is no better angle. The wall is placed vertical. In the second picture, the better angle is also provided. You can see the non-one geotech cell being placed on the interface of soil and Gabion system. Everywhere, Gabions are porous and they can drain freely. Therefore, there is no need to provide any additional drainage system. Non-one geotech cell will be provided here. As per IS 116, base width of the Gabion wall of height up to 6 meter will be in the range of 60 to 75% of the height, and in the range of up to 6 to 10 meters, the base width here to here will be 55 to 65%. But this is only the guideline. This is not the limitation, or not the this is not the limitation. We can design, and because in the higher seismic conditions or the high surcharge loading, we need to have sometime we need to have higher bandwidth as well, as per the which should satisfy the design requirement. Again, the better angle as per codal provisions, or we can say the guidelines, because it is special. It is coming into this special publications. So the better angle should range from 3 degree to 6 degree with the vertical. But again, as we saw in the previous slides, the pictures, the wall can also be designed without better angle, depending on the site requirement. Minimum embedment depth. The embedment depth is the JED here, which is minimum embedment depth here. Embedment depth, minimum embedment, 500 mm for height up to 6 meter, and 1 meter for height up to 6 to 10 meter. Whenever there is a height requirement of more than 10 meter, Gabion fascia reinforced soil walls should be preferred. There is a separate, there can be a separate discussion on the design of reinforced soil walls that we'll take up later someday. So the porosity of the Gabion units is around 35%, which ranges from 30 to 40%. So why this is important parameter? Because, for example, if the unit weight of a rock fill is, for example, 26 kilonewton per cubic meter, then if I'm considering 65% of the porosity only, then if I'm checking the unit weight of a Gabion unit as a whole, then I'll take the unit weight as a 17 kilonewton per meter cube only, which is a 65% of 26. These are the major type of failures of Gabion wall, which can be overturning failure, sliding failure, internal failure, bearing capacity, and overall failure. Whenever we design Gabion wall, we check uh, all these failure criteria. These are the factor of safety criteria for different loading conditions and different loading conditions and different under the different factors such as sliding, overturning, bearing capacity, internal stability. These parameters are also given in code. We at TechFab India, we have Geo5 software with us for the design of Gabion gravity wall. We do all the internal and external stability checks. We need some basic design inputs such as Gabion wall geometry. So this is not the input that should come from the applicator or the client, but that is the input that should be given in the model. Then again, surcharge loading, then terrain topography, soil parameters for the backfill soil and the foundation soil, then soil parameters, then hydraulic parameters. If there is a waterfront, we need to know the waterfront, then maximum drawdown conditions, we need to check for it. Then peak horizontal and vertical acceleration coefficient that varies with the different seismic zones. Then Gabion wire mesh and boulder specifications. As I told you, the Gabion wire mesh specifications are the unit weight criteria for 26 and 17. Then for the designing, we do the overturning and sliding check as a stability. You can see in the previous picture, you can see the overturning and sliding check. Then for the internal stability, we do the overturning check, sliding check, joint bearing capacity check, joint between the blocks for each and every individual layers. Okay. Then we do the bearing capacity check at the foundation level. Then we do the global stability check. This is homepage of Geo5 software of Gabian module of Geo5 software. Then you can see the external stability, internal stability page, and then this is for global stability check. So this is one case study where we provided abutment protection system using Tectum metal gabions at Sabarmati River in Parli, Gujarat. You can see the non-one geotextile being placed on the top, which is acting as a separator or filter. And then this is also one Gabion mattress being placed on the bottom. This is another case study of 8-meter high Gabion retaining wall, where it was provided for lake protection work at Gujarat. Then in the same project, there was a different location where the combination of Gabion wall and Gabion mattress was provided here. So till now, we have discussed about the design procedure. So now the design procedure of launching a plant remains same for all type of protection system or all type of solutions, be it Gabion or sandfield solutions. And the Gabion mattress protection system we have understood. Now we'll understand the brief about the metal Gabion specifications as the product. Then again, after this, we'll discuss about the other products of the other geosynthetic products that can be used for the riverbank protection system. The Gabions, we have understood a lot about the Gabion in the previous slide, so I'll take it up. I'll quickly I'll finish it. The Gabions are the flexible cages of hexagonal double twisted, heavily galvanized mild steel wires. So these are mechanically woven wires. So we should not confuse it with the other rope Gabions or handmade Gabions. This is machine driven and mechanically woven hexagonal double twisted wires. So all the discussion what we are doing is for mechanical cages, mechanical Gabion wire meshes only, not for the handmade or rope Gabions. The Gabions are laced together, packed with selected stones. They act as a single building block. Apart from the Gabion, the major components are the containers, filling stones, and the filter media. You can see this is how the Gabion box. There are the three types of Gabion units. Can be in the form of box, can be in the form of mattress, and sack Gabion. Other components are the infill stones and geosynthetic filter media. You can see this is the non-one geotextile. This is how it looks like. Non-woven geotextile when placed as a filter and separator behind the wall or any protection system, then it is a woven geotextile. There are three types of wires in any Gabion system, which can be mesh wire. You can see these are the mesh wires, then lacing wires, and then salvage wires. Salvage wires are the thickest of all. Lacing wire is the thinnest of all. So these salvage wires are being connected with the mesh wire using lacing wires. There can be various type of coatings, the Gabion or all the wires like mesh wire, lacing or mesh wire, lacing or salvage. These wires can be zinc coated or zinc plus PVC coated or zinc alloy plus PVC coated. And then mesh type can be 6x8, 8x10 or 10x12. Also, we need to know that this is whenever there is a 90% zinc or 10% aluminum, it is called Gallum coating, I think. And also there is a Gulfan coating also there. When there is a 95% zinc or 5% aluminum, that is called Gulfan coating. Whenever there is a 90% or 10% combination, it is called Gallum coating. So mesh type is 6x8, 8x10 or 10x12. So 8x10 mesh, I'm just taking an example of 8x10 or 10x12, let's say. The nominal size D. So what is the variation in all the mesh types are the dimension D. In the 10x12 mesh type, it is 100 mm. and 8 by 10 it is 80 mm. Now boulder size should be selected based on the mesh type only. For example, for a 10 by 12 mesh type, the boulder size should be 1.5 times of D to 2.5 times of D. Means the boulder size should be 150 mm to 250 mm. It should not be larger than 250 mm. But again, how to decide the boulder size? Because boulder is not a linear or a rectangular or a uniform shape, but it is mostly round to angular. So this restriction of 150 to 250 mm is for the least lateral dimension of the boulder. So the least lateral dimension of the boulder should be from 150 mm to 250 mm. So these Gabion boxes are transported in the collapsed form, and then they are in this way, and then they are restructured to the required dimensions using lacing and salvage wires. Gabion units are equipped with vertical diaphragms. You can see the diaphragms at every 1 meter. These diaphragms will allow you to do the rapid filling and maintain the shape of the gabion after filling. Salvage wires are used at every edge of the gabion unit, which are used to tie the gabion mesh using the lacing wires. These are the standard dimensions of the gabion, textile metal gabion. But again, they can be customized based on the site requirements. Gabion mattress is nothing different than the Gabion box, but only difference is it is relatively smaller in height as compared to the other dimensions. Gabion mattresses are used on the riverbank side slopes to protect the bank erosion. The major function of the Gabion mattress is to protect the bed from the excessive score. Sag gabions are the now coming to the third part of the gabion, which is the sag gabion. So sag gabions are the cylindrical baskets made up of zinc coated double twisted wires. They are used as a bed correction element. You can see in this picture, it is used for bed correction and form a stable bed for the superstructures. They can also be used as a sacrificial units in front of the water retaining structures so that they can absorb the excessive wave energy from the seafront or the riverfront. These are the technical specifications of the sag gabions, means zinc plus PVC coating, having mesh size 10 by 12. And sag length is 2 meter and diameter is nearly 1 meter, which is 960 mm. Advantages of the gabion system are they are flexible system. They are monolithic because when they are tied together, they act as a single building block. They are permeable, therefore no need of any additional drainage system. They are durable because they have better coating on the gabion mesh wires. They are adaptable and economical as compared to the conventional solutions, and environmental friendly because we are using only the rock fill items or the naturally available material. Applications can be vast, not limited to these 7 or 8 I have mentioned here. They can be used for mass gravity walls, gabion fascia, RS walls, bed protection system, bed correction system, then wear check dams, railway culverts, launching apron. So now, till now, we have discussed the Gabion system or and the design of riverbank protection system, including the launching apron. All these, whatever we have discussed, are applicable for places where the stones are easily available. Now, we have to find a solution where the rocks are not easily available. So there is a very specially engineered a new system that is called sand-filled geotextile mattress system. It is a double-layered 3D tubular green mattress which forms a protection system over the surface. The upper layer, also the lower layer. Upper layer and lower layer both are made up of high-strength woven polypropylene fabric and mechanically bonded with green staple fibers and cut fibers. They provide the additional UV protections. Uh, Additional UV protection. The most important part is the lower layer should be made in such a way that it provides the base and better filter properties to the mattress system. It should not be clogged during the operation. Geotextile mattresses can be filled hydraulically or mechanically, and also it can be filled pneumatically. But pneumatical filling procedure is not widely used in India. Hydraulic filling is the mostly used here. So it can be filled hydraulically, mechanically with the riverbed material or locally available sand. The tubular shape of the mattress, you can see the tubular shape after filling. In the previous picture, it was unfilled condition and the individual units were being tied. Then this is the separate photo having after the filling with the hydraulic sand filling. The tubular shape of the mattress help in reducing the flow velocity. That is not a big reduction in the flow velocity, but yes, it minimizes the risk of soil erosion because of the reduction in the velocity, and also the bed scoring near the banks only. This protection system also includes the one top anchor trench and one toe trench at the bottom. The top trench and bottom trench will provide you the better placement of the mattress. You can see the picture having a top trench. This top trench can be filled with sand-filled geotextile bags or boulders or with the sand only. The infill soil should be coarse sand. It should not be finer sand because apparent opening size of a geotextile mattress system is usually more than 250 microns. So then the finer soil or the clay particles or the silty particles or the final sand will be washed away. Therefore, the infill soil should be coarse sand and it should be free from organic material. Loamy and clay soil should always be avoided. And as we all know, in any waterfront systems, the water level fluctuate between high flood level or HFL to low water level. This causes the risk of sudden drawdown and seepage in and out of the bank. So because of this problem, we need to have a proper system for pore water pressure release. So it is observed when these protection systems are placed directly on the soil, they have not sufficiently prevented the erosion due to poor filter properties. But this statement is not a general statement, it is only site specific. If the embankment soil or the backfill soil is having a better filter properties, this system will work definitely well. But if it is having a poor filter properties, we need to provide the arrangement for that. So to ensure the success of the protection system on the embankment, which is not having better filter properties, a graded filter, conventional graded filter should be provided behind the behind the geotextile sand filled geotextile mattress. So the graded filter can be 300 thick. So under the conditions where the conventional graded filter system is also not available, then a drainage composite layer should be provided on the profile slope. You can see the picture of this is the picture of drainage composite that can be a direct replacement of conventional filter system. Now under the conditions, so this is applicable only when there is a no impermeability is required. So under the condition where complete impermeability is to be ensured, then one thin layer of LLDP or LDPE should be sandwiched between tech geomattress and drainage composite. So then the direct contact of the soil will be with the drainage composite and tech geomattress will be used on the top, which is in connection with the waterfront. So if an impermeable protection material like LDP or HDP will be provided directly on the profile slope, the bank slope may experience the development of poor water pressure, which is a serious concern. So this is not something that should be directly applied on the slope, but there is a dedicated design methodology of the central geotextile mattress system. We can design the mattress system, which the methodology is called flow load stability method and wave load stability method. I'm just giving one brief of the design methodology, which the design inputs are the channel geometry, hydraulic, and soil parameters. And again, the headline is that it should be applicable on the geotechnically stable slopes only. So after getting the design inputs, we need to determine the design thickness of the mattress. We need to check the launching upon design. We need to check the stability against the longitudinal currents and waves. Then tensile strength of the geotextile, so that we can propose a sufficient tensile strength material on the slope. Then geotechnical stability should be ensured. These are the specifications of TechFab Geo Textile Mattress. The standard roll dimensions are 4.5 by 33 or 5.1 by 33, but again, it can be customized based on the site requirement. Also, the very important point to be noted is after filling, the width of the mattress will be reduced depending on the properties of the infill material and density. You can again go back to these pictures. You can see this is the picture in the unfilled condition. This is after filling condition. So unfilled condition and filling condition, there will be a reduction in the uh, width of the individual layers or the individual pockets. We call it sausages. So the width will be reduced. The reduction is around in the range is in the range of 10 to 15%. But again, it will be decided based on the design thickness or the filling properties. So therefore, whenever we put the geo matrices before installation, we should always provide sufficient overlaps before filling. So it is a flexible, robust protection system. It promotes the natural vegetation growth because it entraps the sedimentations, but it is not a big or a significant vegetation growth. But again, minor vegetation can be grown by entrapping the sediments between the pockets. Then it reduces the pore water pressure. It also gives you resistance to bank erosion, economical, high UV resistance, and aesthetics. The applications can be river bank protection, canal lining, scar protection, shoreline protection, etc. All these solutions, whatever we are discussing, can be applicable on riverfront also and seafront also. The design procedure is a little bit different because in the whenever we design any protection system on a seafront, we need to check the significant height of the wave period of the wave time period of the wave, all these parameters. This is one photograph of the geotextile mattress before filling. You can see the soil. It is ready to be filled inside. There is a bottom trench. This is a very mild slope here. This one typical representation of geotextile mattress on the slope. The top trench of 1 by 1 also being filled with the geotextile bags. Bottom trench of 1 by 1 also filled with the geotextile bag, and then launching apron is also being using the geotextile bags material. This is one case study where we have supplied and installed the geotextile mattress on the banks of Subansiri River in North Lakhimpur, Assam. Maximum bank height is 12 meters there. Slope inclination is 2h to 1b. Then the second case study where we supplied the geotextile mattress at Cooch Behar, West Bengal. You can see the picture, the launching apron being made with the central geotextile bag, and the top trench is also being made using the geotextile bags only. Now coming to the third solution, which is also very unique, and I hope you all will like it. I understand that there is a time. It's already 1 hour, but I request all of you to bear with me for some time. We are having some very interesting products to be discussed. One of them is concrete canvas. So concrete canvas is a class of geosynthetic cementitious composite mat, which is called GCCM. So the total thickness of concrete canvas CCXM is 10.3 meter, sorry, 10.3 mm. So out of 10.3 mm, 0.3 mm is the bottom LLDPE. And then remaining thickness of these three layers are 10 mm. So this is the total thickness of this. You can understand or you can imagine how thick it is. Only 10 mm thick protection system, which is a flexible concrete filled geosynthetic. It is filled with fiber reinforced concrete that hardens on hydration, that hardens after coming into the contact of water. It forms a thin, durable, waterproof layer. It consists of two interconnected layers of geotextile. Two interconnected layers of geotextile. You can see the top one and this one. Encapsulate especially formulated dry concrete mix. This dry concrete mix also fiber reinforced concrete. So it is not just the PCC. It is a fiber reinforced that give you additional protection that doesn't crack actually. And also the LLDP geomembrane that the bottom, it ensures a very low permeability. The CCXM, M represents the mat. So now again, more or less same, but U represents the utility. All the specifications are same, but U doesn't have LLDPE backing. Why it is different? Because whenever you need to apply any slope protection on close to vertical slopes, then you cannot provide the LLDP, the fused LLDP system, because it will not give you the better friction properties. For that, you need to remove that. That is why CCX2 is being introduced. It doesn't have a LLDP backing. It can provide better frictional resistance when applied on the slopes. Whenever there is a mild slope or better impermeability is to be ensured, CCXM should be preferred. Both CCXM and U, they can be hydrated either by spraying the water or being fully immersed in the water. It will attain the maximum strength, which is more than M30, which is more than M30 grade of concrete. It will be attained within 24 hours. It has a very high initial setting strength and low initial setting time, and high final setting. 24 hours is the final setting time, and more than M30 is the final setting strength. Then after M and U, there is a B, which is called barrier, CCX barrier. When there is a absolutely very much more impermeability is to be ensured, 1 mm thick LLDP is to be provided. Test all other properties are same as CCX M and U. You will see the pictures here. CCX M is being used on the slope. This picture is from the South Africa. On the slopes for the slope protection, and this is for the uh, canal lining. The unhydrated unit weight of CCX is around 15 kilogram per square meter. Now you can consider if you are applying a 10 centimeter 100 mm thick conventional concrete, that will give you 200 kilogram weight per square meter for 10 centimeter cured concrete, as compared to 15 kilogram per square meter for the CCX only. So you can see that it is more than 10 times logistical footprints you are saving. So we should not directly compare the cost of concrete canvas as a whole, as a product to product, but the the construction and the life cycle cost as a whole. So it drastically reduces the construction time, drastically reduces the logistical footprints. 24 hours hydration will cure to create a hard wearing concrete lining, which is ready to use. You can see the picture, you can see the video. This is first video in the unhydrated conditions. This is concrete canvas M in the unhydrated conditions. This is how it looks like. And this is in the hydrated conditions. After hydration. So this can be directly applied on the slope for a erosion protection system. It is very vastly used in the mining. Whenever there is a seepage issue in the mining areas, then concrete canvas is the go-to product or the go-to solution in those conditions. And now advantages are it can be very rapidly installed, it attains high early strength, it reduces the seepage. It is a composite solution. You just need to control and add water. And also, when I'm saying add water, just don't rely on rainwater. We should always ensure uh, completely submerged conditions. If not complete submerged, but 100% wet conditions should be ensured. It prevents the clog due to fiber reinforcement. It minimizes the infrastructure downtime. These are the application and some photos of channel lining. You can see the concrete canvas channel lining. Then slope protection for concrete canvas slope protection. Then burnt lining. These are the, again another photograph of channel lining. This is concrete remediation, being concrete canvas being laid on the top of broken concrete. Then can also be used for weed suppression. So it is all up to us. We have a solution, we have a product, we have a solution with designated technical specifications where we need to use it. It is all up to us. So it can also be, you can see the weed suppression is very big problem in many industries. So it can be used here also. So now I'm coming to geotextile bags. Geotextile bag or geotextile containers, they are designed to be filled with sand so that they form a stable and durable protection system. They are small volume containers usually filled at the site and placed on the slopes of water channel, either in the dry conditions, means above the water level, or in the submerged conditions below the water level, on the slopes and also on the river bed. There are two IS specifications are mentioned. The specifications for non-woven and woven geotextile bags are mentioned in IS 16653 and 16654. And TechFab geotextile bags are BIS certified that satisfied all the design requirement and material specifications mentioned in the IRC, sorry, IS 11653 and 54. The volume of geotextile bag, it ranges from 0.05 meter cube. Means it can range. You can make it as small as possible or as large as possible, but should be feasible. So the volume can be 0.05 meter cube to 5 meter cube, depending on the filling density and size of the bag. The geotextile bag can be manufactured by woven geotextile or non-woven geotextile, both. Generally, the large size bags means 2 by 1.5 or maybe higher than that. The larger size geotextile bags are usually manufactured by woven geotextile only, high strength woven geotextile only. These bags provide higher stability, durability against the harsh environmental conditions at riverbank and seashore. The standard dimensions of the bags are 2 by 1.5, 1.5 by 1, 1.03 by 0.70. But again, it can be customized based on the site requirement. The thickness of 1 by zero point 0.7 size geotextile bag is around 150 mm. However, the thickness can vary depending on the filling density. As per the guidelines provided by CWC, which is in the Handbook of Flood Protection, Anti-Erosion and River Training Works, the weight of filled geotextile bag of size 1.1 by zero point 0.7, having filled thickness as 150 mm, the weight is 126 kilogram, which is usually stable up to the velocities of 3 meter per second. For any river water conditions or the flow conditions having higher velocity than 3 meter per second, we need to check the size, and higher size geotextile bag can be provided. These are the technical specifications of PN40 geotextile bag, which is 400 GSM. GSM is the gram per square meter. GSM is the gram per square meter. 400 GSM geotextile bag technical specifications of TechFab geotextile bag. This is one case study of TechFab geotextile bag application where we supplied in Lakhimpur Kheri, Uttar Pradesh. You can see these pictures. Another case study where we supplied and installed. These are very limited. I've just brought one or two case studies of every solution, but there are ample amount of case studies. If you need to know more about these case studies or any other locations, you can always contact to us at any time after the presentation. So the another case study is the riverbank protection with geotextile bag at Brahmaputra riverbank in Tinsukia in Assam. So where we supplied 10 meter bags for 10 meter bank retention. The slope inclination is 2h to 1b, and then you can see that the launching apron is also being made using geotextile bags. So this is the construction procedure at the time of installation at Tinsukia, Assam. You can see the non-one geotextile being laid. The construction was done during a lean period. This is the non-one geotextile being laid first. Then you can see the launching apron. Then laying of geotextile bags on the slopes. Then you can see the final after completion photograph. The advantages are more or less similar to what we have discussed in other flexible solutions. But means whatever the geotextile geosynthetic solutions are the flexible solution, the advantages are more or less same. So tech geo containers are filled on site locally with the locally available sand. They are flexible. They form a robust protection system. Also, vegetation growth can be promoted by entrapping the sediments between the grooves. It reduces the pore water pressure because of the impermeability. It is economical, efficient, and easy to transport, and UV resistance for shock. Then these applications can be riverbank protection, canal lining, spa protection, flood mitigation. They can be used. You can see this is for the bank erosion protection, but here the geotextile bags are used as a core of the joints. So the cores also can be made with this. They can also be used for the breakwater construction, groin construction for the in the sea surface protection system. Now coming to the last solution or the last product that we are discussing in our today's presentation, which is the sand-filled geotextile tubes. So we can consider geotextile tubes as a larger version of geotextile bags only. So tubes are containment structure made up of woven or geotextile, made up of woven or non-woven geotextile. They are filled at the site with the river or marine sand. Under dry or wet conditions, dry conditions means there is no waterfront. Wet conditions means at least there is a waterfront conditions ahead of the geotextile tube, because it also applies some passive pressure. So we need to take care of the wet conditions while designing. That is why it is very critical to mention it. So geotextile tubes are the mass gravity structure and filled with the sand water mixture. This is also sand water mixture means sand slurry. So it is filled through filling ports. You can see the pictures. These are the filling ports. They can be used in hydraulic pumping. It is filled. The container capacity can vary, as we discussed in the geotextile bags. It can vary from 0.05 to 5, depending on the size requirement. The tubes can also vary from 2 cubic meter per cube, 2 cubic meter per running meter to 20 cubic meter per running meter, depending on the site requirement or the size of the geotextile tube. These tubes allow the excess water, because this is all the materials what we are discussing are the geotextile or the geosynthetic geotextile material. They are having they are not they are permeable systems. Permeable systems are having some apparent opening size on the fabric fascia. So apparent opening size means they are having pores. These pores will remove the water or remove the water from the sand slurry. So these tubes allow the excess water to pass through the pores, while retained fill attains a compacted, stable mass within the tube, and they form a elliptical shape after the filling. So this is how elliptical shape is being attained after the filling. You can see, and you can see the score apron or the Scott tube. Scott tubes are usually installed in combination with the anchor tube. This is the main tube, and in combination with the main tube, anchor tubes are also provided. And non-one geotextile is being provided here up to here, being used as a score apron. Filling ports are provided. Generally, it is provided one filling port at every 5 meter. The diameter of the filling port can vary, but mostly it is 300 diameter, and the length of the filling port we'll see. The diameter of the filling port is around 300 and the length of the filling port is around 1.2 meter. But again, it can vary. But the standard dimensions I'm suggesting to you, it is 1 meter to 1.2 meter. You can see this longitudinal view of geotextile tube. So this is a 15-meter length geotextile tube having three filling ports. These ports are distant 5 meters from each other, and they are distant 2.5 meters from both the ends. This is the cross-sectional view of the geotextile tube, and you can see the maximum pressure is usually applied at or exerted at the bottom of the geotextile tube, because the pumping pressure at P naught, then P naught plus gamma H. These are the mechanical properties of the one of the geotextile tube fabric, which is 100 kilonewton per meter fabric, which is in TFI, we call it TFI 1500 JAD. So as I told you that we do the geotextile, we do the Gabian wall designed with the Geo5 software. Similarly, we do the geotextile tube analysis by GeoCop software. GeoCops, the full form of GeoCops is the geosynthetic confined pressurized slurry. So we need to know some design inputs, which are theoretical diameter of the tube. Means it can be 3 meter, 4 meter, because it attains the elliptical shape. So after the filling, theoretical diameter doesn't have any significance. It is only before the filling. So we need to know the theoretical diameter of the tube, unit weight of the soil slurry to be filled inside, unit weight of the consolidated field after taking the water out, then fluid if it is available outside, then net pumping pressure, then reduction factors. So now design and outputs are consolidated geometry of the tube, required ultimate tensile strength of the tube, and then net pumping pressure. We may confuse that why net design inputs, net pumping pressure is being used as the input and output, because there are different methodologies are given in the software, that if we are if we are filling, if we are providing the input as the consolidated thickness or the geometry of the tube, then the model will provide us the net pumping pressure. If we are putting net pumping pressure as an input, it will give us the consolidated thickness or the consolidated geometry of the tube. So it can be used vice versa. This is output photograph of output of the geotextile tube software of the GeoCop software analysis. This is for the 3 meter height, 3 meter 3 meter theoretical diameter geotextile tube having filled thickness as 1.8 meter. So the filled thickness of any geotextile tube is usually 55 to 65% of the theoretical diameter. But it can be checked while designing. But the general understanding is the field thickness is 55 to 65%. So if it is a 3 meter theoretical diameter, then the field thickness is like around 1.8 meter. If it is 5 meter, then the field thickness is around like 3 meter. So typical representation of seashore protection. Again, what we discussed till now is for the single layer geotextile tube. But geotextile tube embankment can also be formed by stacking the tubes over one another. You can see this typical cross section where total 9 meter height retention was required, out of which 5.5 meter was done with the geotextile tubes, and rest was done with the soil embankment. You can see the bottom layer is with the 3 meter diameter tubes, which is 1.6 meter filled thickness, and then 1.3 meter diameter, 1.3 meter final thickness with the 2.5 meter diameter tube. So 1.3, 1.3, 1.3, and 1.6. It makes 5.5 meter embankment with the geotextile tube, and rest of the embankment was done with the soil embankment only. This is one case study where we supplied geotextile tubes at Dahanu Beach in Mumbai, Maharashtra, of 3 meter theoretical diameter. 1 meter anchor tube was provided. You can see in these pictures. This core apron was provided. This is another case study of restoration of eroded beach at Kattupalli, Chennai, where the total height of the protection required was 7 meter. Now we can understand the 7 meter height cannot be achieved by single tube, because the field thickness can be only 5 to 6 meter. Sorry, 50 to 6, 55 to 65%, or we can say 60%. So then the theoretical diameter requirement will go more than 10 meters. So it is not, it can be theoretically possible, but practically very difficult. So that is why we need to stack the tubes over one another. So the requirement was for 7 meter height retention. Height of the protection achieved by GO2 embankment was 4.8 meter, and then rest of the height was attained by, again, the slope. Then 3 plus 2 plus 1 type structure was provided by 1.6 meter. I'll show you one cross section. You can see the total 7 meter requirement was there, and then 4.8 meter was provided with the tubes, and rest was the geotextile tube, soil embankment. There is a score tubes also, anchor tube also. In this Kattupalli case study, this is the for the construction of base layer. You can see the three tubes. We can see here the three tubes are being placed behind each other. This is the construction of middle layer after filling of these three tubes. Yeah. So the advantages of geotextile tubes formation, they can be used for sea shore protection system or land reclamation. These are economical, ecological, coastal, and riverbank protection system. High positional stability because of the mass gravity structure, the large mass gravity structure. They are highly UV and abrasion resistant. They can be filled with the locally available sand. It allows the rapid and economical filling, multifunctional in applications. Why I'm calling it multifunctional? Because sometimes there is a uh, application called dewatering and sludge disposal. So at the geotextile tubes can also be used at the sewage treatment plant at the end product for the sludge disposal. It can be used for the dewatering also. So the applications can be coastal protection, riverbank protection, spore apron, for soil erosion control, dewatering, river groins and spurs can be used as a core of river drain spurs. This is one just comparison of different protection systems for riverbank protection. You can see this is how unprotected riverbank looks like. Then it is a riverbank protection with gabion mattress. Then this is unprotected. This is protection system with geotextile bags and with the geotextile tubes. This is all for. So these are the references and codal provisions I've used for this presentation. So this is all from my side. Thank you. Thank you so much, everyone, for your patience. I'll be happy to take the questions if there is any. So I'll take the questions one by one. So one question is about how to find out the HFL, the highest flood level. So first of all, thank you for questions. But whatever we discussed is for the protection system. But still, I'll answer your questions. The HFL value uh, can be checked or determined. First of all, there are various methodology available. First of all, there are we need to check the previous data record of any particular site location. There can be river markings or nearby markings on the bridge piers. They are very they are very good representation of HFL marking. So this is one way of getting that. Second way is like CWC provides the data. Third way of getting that is to check the analysis. If we have the design discharge, then we can also check with the Manning's formula, like area into velocity, and then again we can vary the height, and then it can be HFL can be only indeterminate thing remains is the height of the water. So if we know the design discharge, then we can cross verify the HFL. So we should at least know one thing. If we know the HFL, we can determine the design discharge. If we know the design discharge, we can calculate the HFL. Uh, the question is, if you want to do the seeding, need greenery, then which material is preferred if slope is 1:1.5? See, if the slope is 1.5, first of all, the soil should be stable, or if whatever the solution we are providing, it should be applicable on the geotechnical stable slope. And if the only objective is to provide the seeding, then there are some like quiet mats can also be provided, and some vegetation can be grown here. But the geotextile sand matrix system will give you the vegetation growth, aesthetic looks, and also the riverbank protection system. So in this condition, first of all, we need to know the site requirements as a whole. But either the if the vegetation growth is the only objective, then quiet mats or the vegetative soil mats can be provided, or the geotextile sand matrix can be provided. One question is the 3 meter by 20 geotube outer failing height. So the 3 meter means the theoretical diameter of the tube is 3 meter. So in this case, the filled thickness will be achieved in the range of 1.6 meter to 1.8 meter. So 1.6 meter to 1.8 meter can be achieved after filling. See, the objective is to store the water. For the water storage, you need a complete impermeability, right? So water storage, if whatever I have understood from your question, is you need to know about the water storage. If it is inside the pond, then you need to know the geotextile liner. You need to provide the geotextile liner inside, and then on the surface you can provide Gabion mattress protection system if you have the stones available, or then the geotextile bag or geotextile sand mattress. So for protection, you need complete impermeability, and any single geotextile system cannot give you the impermeability. So if the objective is to provide geotextile system, then complete impermeability can be provided with geotextile liner and then sand filled mattress. Otherwise, the best solution for storage of a pond or reservoir is to provide the concrete canvas. What I showed you, the CCXM can be applied throughout the slope all around the reservoir. That will give you complete impermeability and storage, and then it can be used and lift in the summer season. So what about providing pile cap for score effect? Yes, definitely pile cap will be provided for scoring it is not provided for scoring effect actually. It is provided to support the pile foundation. But our objective is that any kind of foundation should not be exposed. If the pile cap is also provided, the bottom of the pile cap should be below the maximum anticipated score depth. If it is well below the maximum anticipated score depth, then there is no problem. But if the already constructed foundation is above the maximum anticipated score, then we need to provide additional protection system. Not possible 1.6. No, actually, see, 1.6 and 1.8 can be provided. Definitely, it can be achieved. And 1.25, that's not a problem. See, 1.25, 3 meter with the 3 meter geotextile tube, definitely 1.6 will be achieved. See, let me tell you the details of the design. Whenever there is a difference between the filled slurry and consolidated slurry, the unit weight of the filled slurry, just for example, if it is 13 kilonewton per cubic meter and unit weight of the consolidated slurry is 13.5 or 14 kilonewton per meter cube, then you can achieve whatever the designated height you want to. If there is a drastic change or drastic difference between the filled slurry or consolidated slurry, then definitely you will get a lower height. That is the reason why it should be designed. We need to know what is the unit weight of the filling slurry and consolidated slurry. So lesser the thickness, lesser the difference between unit weight of filled slurry and input slurry, then higher the thickness. If there is a large difference, then you will get the lesser height. So if you are getting 1.25, that means the difference between unit weight is huge. The next is it effective for the protection of coastal roads which are very close to seashores? Yes, I'm not understanding for what kind of solution you are asking for the seashore. Yeah, definitely the Gabion mattress system can be provided on the seashore coastal roads. You can see in many places already it is being used, and definitely geotextile bag, all kind of solutions can be provided. Recently, at one of the locations in Kerala, we have provided a total 3 meter height geotextile tube for coastal road protection system in Kerala. So it can be definitely used. What would be 1 cubic meter Gabion packing density? Yeah, 1 cubic meter Gabion packing density will be 17 kilonewton per cubic meter. Yeah. Sorry, I'm not understanding the question. Size 1 by 0.75 meter, 1 cubic meter, use geobag quantity. Should we provide ACBM for 1:1 slope? Can you just elaborate? Or better, see, we have already exceeded the time what we have designated for this presentation. So I request all of you, if you have any questions, you can anytime you can just uh, send a mail to Jisha, what you have got the mail from, and also you can send it to me. You can write my mail ID, which is s.garg at techstabindia.com. You can uh, write your questions or your queries to my mail. I'll definitely answer your queries. Thank you so much for your precious time.